Assalamu alaikum wa rahmatullahi wa barakatuhu. Rabbi shrah li sadri wa yassir li amri wa hlul uqdatam min lisani yafqahu qawli. So in today's video we will start our new chapter of electric machinery, which is about the particular DC motors and DC generators. So as we know that initially the power system was DC, and then AC was developed, and then AC motors were developed, and so on. But the DC motors actually lost their popularity in the beginning, but still they are popular again because of certain reasons that they can be used in various equipments till now, in robotics and in cars, trucks, and aircraft. So, and all those some of the systems where the power DC power system is there. So that's why we must have very deep knowledge of these DC motors. So because DC motors application is again widespreading because of their high speed and everything. All the RC, if you see quadcopters, they have the DC motors with the high RPM of around 12,000 RPM or 11,000 RPM. That's easy for the DC motors to attain this much RPMs instead of having the huge induction motors or other synchronous motors for which we have to change the frequency to attain such a high RPM or the high speed. So before the widespread use of electric power rectifier inverters, DC motors were unexcelled in speed control applications. Now, because we know that the power electronics and solid state drives, solid state electronics has very popular, and it has a tremendous research in this field. So we have a vast field, vast means equipments to control the speed of the DC motors and also the torque of the DC motors. So we can control both of these parameters of DC motors. So today, induction motors with solid-state drive packages are preferred choice over DC motors for most speed control applications. However, there are still some applications where DC motors are still preferred. So, DC motors are often compared by their speed regulations, and we know that speed regulation that we have studied already. It is the ratio of the speeds, and the numerator we have the speed, no load speed minus full load speed, and if we divide it by the full load speed, that will be our speed regulation. And because of their internal structure and their somehow use or the applications or how we treat them, DC motors can be classified into the following major classes. The first one is the separately excited DC motor, the shunt DC motor, the permanent magnet DC motor, the series DC motor, the compounded DC motors. So for this course, we will assume that the DC input voltage to the motor is constant, because this assumption makes our analysis of the motors easy and the comparison between different types of motors. So we will look these motors one by one. Let's look at the equivalent circuit of the DC motor first of all. So that will be here. We can see that because we know that we have the two circuits here. One is the field circuit, and we can provide the DC voltage here. This R variable resistor is also inserted to control the current flowing to the field circuit. And this is our armature circuit, and this is the brush voltage drop. Normally it is assumed very small, so sometimes we ignore it and we use this formula, oh sorry, this figure to represent the DC motor. And also this sometimes this adjustable resistor and this field resistor itself that is accumulated in it. Now we have there must be a question that why there is no inductor in here. So because we have kept it variable and we have made it constant, so at the constant DC voltage we know that inductor has no effect, so that's why we have removed it. But if we will going for any dynamic analysis, maybe in your next few courses, advanced courses, you will see that that if you have the inductor, then we will be having the resistor here. But as we know from our basic knowledge of the derivatives, that for the constant input, derivative has no effect. So that's why similarly, if for this inductor, sorry, here this inductor is not here, but here this inductor is shown because we are assuming that we can change this IF at any time. So the armature circuit is represented by an ideal voltage source EA and a resistor RA. The brush voltage drop is represented by a small battery V brush opposing the direction of current flow in the machine. So the field coils which produce the magnetic flux in the generator are represented by inductor LF and resistor RF. The separate resistor R adjustable represents an external variable resistor used to control the amount of current in the field circuit. So the brush drop is very often only a very tiny fraction of a generated voltage in a machine. So therefore, in cases where it is not too critical, V brush may be left out for or approximately included in the value of RA. So normally we do not means put this V brush until or unless it is very high. Now we know that the internal resistance of the field coils is sometimes lumped together, and the variable resistor and the total is RF. So that's how we know that. The third variation is that some generators have more than one field coil, all of which will appear on the equivalent circuit. So the internal generated voltage, we have seen here this one previously, that EA is equal to K phi omega M, and we know that the K is the machine constant. These are the parameters of the machines. Similarly, the torque developed by the machine is torque induced is equal to K phi Ia. So these two equations and the KVL that we can write here of the armature circuit of the machines, a magnetizer core, are all the tools necessary to analyze the behavior and performance of the DC motor. So we will be having these three equations: EA is equal to K phi omega M, T induced is equal to K phi Ia, and this third one, this KVL equation here. So obviously, as we know that this is the magnetization curve of a ferromagnetic material, and we know that it does not complete the whole hysteresis loop, because this is of a DC nature, because we have the DC input. So it can go to the saturation here. So on this axis we have the 5, and this is the MMF, which is ampere turns. And similarly, we can plot the curve between EA and IF, and this is omega naught or n naught. We are assuming at a constant at a certain one speed. So the machines are designed to operate near the saturation point on the magnetization curve. So this implies that a fairly large increase in field current is often necessary to get small increase in EA when operation is near full load. Means it is this point. So if we want to increase EA, or if you just look at here, if you want to, we are operating in the saturation region. So if we want to increase EA by a small value, so obviously we can see that we have to increase it in a very big value. So IF must be increased in a huge amount to get the EA increased of this motor. Now let's look at the separately excited DC motors, and here we have written this KVL equation, which is equal to VT, which is equal to this voltage drop plus IA RA. Now again, remember that this is in the steady state form, so that's why we don't have the inductor here and no derivative in this equation. And we are assuming it as just IF. This is a kind of a source which is providing field current to this to generate this voltage. So sometimes, so already we have seen that sometimes we lump them together to make it just single RF, unless or otherwise specified that we are varying the IF, or we have certain values for certain IF. So a separately excited DC motor is called separately excited DC motor because we have to use two power supplies. One power supply is used for field circuit, and the other power supply is used for the armature circuit, or we call it as the terminal voltage. Okay, so we have to use two sources. That's why it is called the separately excited DC motors. Now this is a shunt DC motor. Shunt is just like this. If we just put the if we just make the adjustments of these power supply such that the field circuit becomes in parallel with this terminal voltage or with the voltage we are applying to this armature, and then the armature is in series, and then we have this kind of configuration. So we call it as the shunt DC motor. So this becomes the shunt. But if you remember that IF will be simply VT over RF because we are assuming that a constant we have applying a constant voltage. We are not dealing with the dynamic behavior, so that will not be reflected here. So similarly, this KVL is same here as we have seen for the separately excited motor. So VT is equal to EA plus IARA, and similarly now then IL will be simple the sum of these two currents IA and IF. So this is armature current and this is the field current. So a shunt DC motor is a motor whose field circuit gets its power directly across the armature terminals of the motor. There is no practical difference in behavior between these two machines, means separately excited and these shunt DC motors have not much big difference in them. The only difference between them is that for the separately excited DC motors, we have the capability to control IF separately and IA separately, means we can control the torque here from IA because we know the torque equation is K phi IA, and we can speed the control because this IF will be generating voltage, and that is a K phi omega m. Sorry, we can control the IF to increase or decrease the speed separately. But that is not the case here. But that is the another scenario that we are not discussing in this course. But that's why we are assuming that their basic behavior of operation is similar. So these are the torque speed characteristics of this motor. As we can see that if here this if there is no so if it means if it is a zero speed, still we have a zero sorry, if we have speed this then we have zero torque, and then as the load is increasing, so this is a no load speed, and as the load is increasing so the speed is also decreasing with it. So what happens to this, the load torque will exceed the induced torque so in the machine, and the motor will start to slow down. So as the load will increase, it will slow down, and as slow down we know that E is equal to K phi omega m, so EA will decrease, and if EA will be decreased, so from the KVL equation we have written on previous slide, so from that equation we can find this IA, which will be then VT minus E over RA. So that will, if EA will be increased, so obviously IA will be increased, and if IA will be increased, so torque induced will be increased. So torque induced will be settled where when at the load torque. So this KVL equation of the armature side, we know that here, and EA we know that it is equal to K phi omega m, and torque induced is equal to K phi IA. So if we just bring out this IA from here, so it will be torque induced over K phi, and if we plug this IA here and the value of EA, which is K phi omega m here, so we can write down this equation. If we just take out this omega m on the other side, then this equation will be just like a straight line with the y-intercept here, and this is the negative slope, and don't bother about this square because K phi is constant here, so constant square is again a constant, so we don't have to worry about this constant. So this will be a equation of a straight line with the decreasing slope. Slope is decreasing with this ratio, as we know that, and this is just an equation of a straight line. Let's look at this figure, and here it's only shows that if there is no armature reaction, so it will be a ideal like this straight line, and means if we have some compensation winding or some methods that we have seen to reduce the armature reaction effects, and if we don't have these if we have this armature reaction happening in our machine, so this curve will be slightly curved like this. So the speed for the speed of the motor to vary linearly with torque, the other terms in this expression must be constant as the load changes. So we are talking about this equation. So we want to keep everything constant. Only the load is allowed to increase. So the terminal voltage supplied by the DC source power source is assumed to be constant. If it is not constant, then voltage variation will affect the shape of the torque speed curve. So we are also assuming that Vt is constant. Another fact internal to the motor that can also affect the shape of the torque speed curve is armature reaction. So if motor has armature reaction, then it's as its load increases, the flux weakening affects reduce its flux. So the effect of a reduction in flux is to increase the motor speed at any given load over the speed it would run at without armature reaction. So if motor has compensating windings, of course there will be no flux weakening problems in the machine, and the flux in the machine will be constant. And if a shunt DC motor has a compensating windings so that its flux is constant regardless of the load, the motor speed and armature current are known at any one value of the load, then it is possible to calculate its speed at any other value of the load. And similarly, if the armature current at that load is known or can be determined. So I hope you have understood so far about these DC machines, why DC machines are still used, and we have seen only for the time being two types of the DC machines. One is the separately excited DC machine, and the other one is the shunt DC machines. So still, if you have any questions, please feel free to ask. Stay blessed. Assalamu alaikum wa rahmatullahi wa barakatuhu.